Right, so we come to the last part of surface tension and viscosity. Let's start with the property of surface tension. Surface tension is a very interesting property of liquids, which demonstrates the fact that the surface of a liquid, the open surface of a liquid, is actually like a thin elastic layer and has the ability to apply restorative force and store elastic potential energy. So it's a property of all liquids which has to do with the nature of its surface and the underlying root cause of it being again the nature of the intermolecular interactions, or in this case they are called the cohesive forces, that is the attractive forces between like molecules. So let's start with this part. So surface tension is the elastic property,
So we have to copy, no?
yeah, of a liquid surface. Due to the nature of the cohesive forces that act between the molecules at the surface. So by cohesive forces, here we mean the intermolecular attraction forces between what we call like molecules. Molecules of the same substance. So this elastic nature of a liquid surface can be understood from certain observations in everyday life of physical properties. For example, you can see that lightweight insects can literally walk on fluid surfaces without any part of their body submerged, which means that their weight is not getting balanced by any kind of buoyant force. They are not floating, but literally they are walking on an elastic surface of the liquid, because being lightweight, their weight can be balanced by a restorative sort of elastic force that is created as the body weight of such an insect creates a deformity in the liquid surface. It dents the surface a little bit where the weight is acting on it, and that denting causes a restorative force to act, just like uh, an elastic membrane, or you can visualize a thin rubber sheet stretched out would support light weight placed on it. Like that, a liquid surface is able to support the body weight of a light insect, and we see many such species of insects which literally walk or move about on liquid surfaces without any part of their body submerged, which means that they're not floating. They're literally walking on the surface of the liquid. So that again happens because of the elastic nature of the surface, which we will quantize later as surface tension. So the first observation from everyday life that we see, which gives us this idea about the property of elasticity that a surface has, is this one, that lightweight insects are able to walk on liquid surfaces without any part of their body submerged. So what happens here is that the weight is supported by or balanced by elastic force that the surface applies. So once again, you can see that the surface acts like an elastic material. Another evidence of the elasticity of the surface is the propagation of transverse mechanical waves that we observe on liquid surfaces, like ocean waves, okay, or gentle waves on the surface of a pond, okay, etc. So these mechanical waves are able to exist only because the surface has elasticity. So oscillations created on a liquid surface cause propagation of energy in the tangential direction, that is along the surface, while the surface molecules themselves are only oscillating normal to the surface or in the vertical direction. So this kind of wave propagation, or what we call transverse wave propagation, transverse mechanical waves, which are caused by vertical oscillation of liquid molecules at the surface, causing energy or mechanical oscillations to propagate horizontally or tangentially on the surface. This is again possible because of the nature of the surface, the elasticity that it has. It causes the propagation of such oscillations and waves. So the existence of transverse mechanical waves. Just a moment. Yeah, so the existence of transverse mechanical waves that propagate on the surface of water bodies, whether we talk about ocean waves or waves on lakes, ponds, etc. So they are able to propagate because of so there is propagation of the waves which happens tangentially, that means along the surface. Due to oscillation of surface molecules normally or vertical, okay, while the tangential direction is horizontal. So again, this oscillation of this surface molecules. This is able to happen because of the elasticity. So oscillation occurs due to the elastic nature of the surface. So these are some everyday examples which show us that a liquid surface has this property of elasticity, which might appear a little strange in the beginning, because it's after all the same set of molecules which is present inside the volume of the liquid, in the body of the liquid. But why the molecules at the surface are behaving in a different way? They act like a layer which is elastic, which is separating the volume of the liquid from the surrounding environment. But we'll understand soon that it is because of the difference in the situation of the molecules at the surface in terms of how they experience cohesive forces or intermolecular attractive forces compared to the liquid molecules which are inside the body of the liquid or within the volume. So there's a difference in how the cohesive forces cause interaction between molecules at the surface versus the molecules inside the volume. And that is what creates this unique property that the surface molecules have, that they act like a thin layer which is elastic in nature. Okay, so let us understand the yeah, we will discuss about Poisson's ratio also. Okay, so I'm just showing the notes from the beginning once. Yes, Durgesh, cohesive forces are intermolecular attractive forces, but between like molecules, that is, between molecules of the same species. So, for example, if you have, let's say, a solution which has water and some dissolved salts, then the intermolecular attractive forces between water and water molecules, they will be called cohesive forces. But the intermolecular attractive forces between, let's say, the sodium ions and water molecules or the chloride ions and water molecules, they will not be called cohesive forces, rather they will be called adhesive forces. Okay, so in general, when we talk about intermolecular attractive forces, we talk about two types, cohesive and adhesive. So cohesive is the attractive forces between the like molecules, that is molecules of same species or the same substance. And adhesive is between different substances or unlike materials. When we discuss about contact angle later, we will see how adhesive forces plays a role also. But right now we're discussing purely about the surface tension of a liquid. And very soon we will see that it is because of the nature of the way cohesive forces act at a surface, that the surface has this property of being elastic in nature. And that elasticity is measured by its what is called surface tension. So surface tension is a physical parameter or it is a material property, like modulus of elasticity or coefficient of thermal expansion or density or things like that, tensile strength, etc. So like that, surface tension is also material property. So before all this, before we come to this, let's look at the proper definition of a surface. We just talked about the term surface very loosely right now. So the definition of a surface of a liquid has to be defined very precisely. That is nothing but a very thin layer of molecules that separates or acts like a boundary between the volume or body of the liquid and its surrounding environment. So when we say thin layer, what we mean by it being a thin layer is that the thickness is of the order of a small multiple of molecular diameter. So typically we are talking in fraction of microns, extremely thin layers. Okay. So an example of a surface would be, for example, the open cylindrical or the open surface of a liquid in a cylindrical vessel, which separates the body of the liquid from the surrounding air or atmospheric air. That would be an example of a surface. So imagine this open cylindrical vessel, like a glass vessel or something, and you have a typical liquid like water or soap solution or something like that in it. So you can visualize a thin disk, like a thin membrane of liquid molecules at the surface, which separates the volume of the liquid from the air outside. So even though it's the same species chemically as the volume of the liquid, whatever the volume of the liquid, same molecules are present at the surface. But because of the nature of cohesive forces at the surface, we'll see that the surface itself acts like a thin, boundary layer, which is elastic in nature. So for example, if there is a strong wind blowing, you will see that that surface almost like jiggles, it oscillates like an elastic material. Or an insect can walk on the surface and move past it. So that entity or that physical quantity is called a surface. So a thin disc-shaped surface of fluid. In case of an open cylindrical vessel with fluid. Another example would be, now this is something very interesting. If we have a volume of liquid in zero gravity environment, it takes the shape of a sphere. It takes the shape of a solid sphere. So in a zero gravity environment, like outer space or inside an orbiting space station, etc. Okay. So this volume of liquid always takes a spherical shape. In zero G environment, it takes a spherical shape. And the body of fluid is separated from its environment through a thin spherical surface. So it's like a thin spherical shell. So that is the surface. Okay, so these are two physical examples of a surface of a liquid. Okay, Samar, the meaning of this statement, the order of a small multiple. That means if you take the thickness of the liquid layer, like you imagine this is the thin layer of liquid at the surface, which we are calling the surface actually. The surface is this thin layer. So the thickness of this layer is D. So D's order of magnitude is some n times the molecular diameter, where n is a small number, like 10 or 12 or something like that. So it is very small in thickness.
So each liquid का differ तो करेगा ना?
Sorry, come again.
Through material property, surface का मतलब.
Yes, it is a surface tension is a material property. Yes. Okay, so imagine a very thin layer of liquid at the surface, whose thickness is so small that it is a few times the diameter of liquid molecules, few times the molecular diameter. That kind of a thin layer is called the surface of the liquid. So now let's understand surface tension, the property of its elasticity on the basis of cohesive forces. So if we take our first example of a liquid surface, where we considered liquid in some sort of an open vessel. Now compare the cohesive forces that are acting on a liquid molecule at the surface versus cohesive forces acting on a liquid molecule inside the body of the liquid. So at the surface, the cohesive forces which are acting are like this. So they are more predominant tangential to the surface. Whereas inside the volume, the cohesive forces are sort of balanced equally in all directions. Okay. So this is what creates the property of surface tension. So now, for example, if I were to place some object on the surface of liquid, causing the surface to get slightly bent. So this is another experiment that all of you can visualize. You have something like soap solution, which because of these soap molecules along with the dissolved in the liquid, it has more strength of surface tension compared to just water alone. Now you take a thin metallic needle and place it very gently at the surface. Okay. So you are able to balance its weight. So a thin metallic needle balanced at the surface. So how its weight is balanced, even though density of the metal is definitely more than the density of the solution. So it cannot be floating, but yet we observe. So if you put the metallic needle inside the volume of the liquid, you'll see it definitely sinks. But if you place it gently enough at the surface, you're able to keep it in a balanced position. So that happens because if you observe closely at the surface where the needle is present, you draw sort of magnified diagram of it. Think of the needle like a thin cylinder like this. You'll see that the surface has got a little bit contorted like this, like a membrane would get contorted. If you draw a very magnified diagram of it, you'll realize that if this is a cross section, magnified, the position at which that needle is lying on the liquid surface, it causes a sort of an indentation like this, the liquid surface there. So the indentation causes these tangential cohesive forces to act like this, which in turn creates a net force in the upward direction. because of these tangential cohesive forces. At the surface. So that creates a net restorative force, which exhibits the elasticity of the surface. So this elastic property, or what we call surface tension of the liquid, it has a sort of tension. It's like a stretched out layer, thin membrane kind of thing, which has a tension or an elasticity to it. It's because of the nature of how the cohesive forces act tangentially at the surfaces of any liquid. Okay, now let's understand the definition of the term surface tension technically. So there are two ways of defining it actually. I mean, we've already understood that it's associated with the elasticity. Surface tension is generally denoted either by T or in some cases capital S also. So this is the tangential force per unit length that is experienced by liquid molecules at a surface, and it is a material property of a given liquid. It is measured in newtons per meter. More practical unit is millinewtons per meter. So basically, if you visualize any surface of liquid, so this is the top view of a surface of liquid. Then visualize any line of liquid molecules. They are experiencing tangential forces on both sides like this. So that tangential force per unit length is surface tension. That's basically because of the action of cohesive forces. Between molecules. So that tangential force acting on a line of molecules of length L at a surface, that is Ft. So that per unit length, that is what we mathematically define as surface tension. Just to give you some examples, the value of surface tension for common fluids like example benzene has a surface tension of about almost 29 millinewtons per meter. Then, for example, formaldehyde.
So we need to
No, you don't need to remember. I'm just giving you some examples. About 58 millinewtons per meter. Mercury has one of the highest surface tensions. The only known liquid metal is about 420 something, 425.
So what about gallium?
Just a minute. Water has also got a reasonably medium kind of surface tension. Water has about 73, 72.8. Yeah, which material you are talking about, Beta?
Gallium. Gallium is also liquid, no?
Gallium.
Gallium is liquid metal.
So gallium has a fluidic kind of structure, but it is not technically a liquid.
Okay. Okay, sir.
So elemental gallium is very soft. So it's got the very high amount of ductility and very low tensile strength and all that. Okay. But it is not exactly liquid at room temperature.
It's semi-liquid, you can say.
Yeah, it is more like it's like powdery. In that sense, even francium and cesium are semi-liquid. Gallium can also be called semi-liquid. That's correct. So anyway, these are just examples of values of surface tension. You don't have to memorize these values.
Yes, sir.
Okay, so we will see an example problem based on this. So this is an example based on that situation we were just discussing about, that you have a liquid surface on which very thin object like a thin metallic needle is sort of balanced. So this is a liquid surface. So obviously, like there is some liquid in a container like this. Now there is a thin metal needle kind of thing. Now what happens is that when we magnify the cross section, what we are observing, just a second. Yeah, so when we magnify the cross section, what we are observing is that the surface of the liquid has got bent under the weight of the metallic needle. So if this is the magnified cross section, what we are observing is that where the surface has got bent, so this is the shape of the surface. So like in three-dimensional diagram, this would look a bit like this. The surface of the liquid has just got a slight bend. This over here. So there, if we draw tangent at the point of contact, that makes an angle theta on either side with respect to the horizontal. So at the line of contact, the tangent to the surface makes theta equal to, let's say, 15 degrees, or let's make it smaller, 7.5 degrees with respect to the horizontal. So if the surface tension of the liquid is 125 millinewtons per meter, and the length of the rod or the needle is equal to 5 centimeters, then we want to find its mass. Okay, so here what we'll have to understand in this type of question is that if we look at the top view of the needle, then it will be experiencing in this diagram what will look like forces which are perpendicular to its length, like this, because of surface tension on either side. Okay. But this diagram is a little bit misleading because the surface is not flat. Okay, so this is what the top view will look like. But when I consider the cross section from the side, it will not look like this. When I consider the cross section from the side, these forces will be acting like this. They will not be acting horizontally. They will be acting tangential to the surface. So they'll be acting at theta. And of course, the weight of the object will be acting like this. So this is the equilibrium condition. So you can see that Ft is the force due to surface tension on a length L. So it is surface tension into length. Okay. So this is tangential force on length L at the surface. This is in contact with the liquid molecule. So the liquid molecules are applying surface tensional forces of total magnitude F into L from either side like this. Okay. So based on this, now you can work out. Okay. Now here you will use the small angle approximation. So you use the fact that sine theta is approximately theta for small theta. But remember here theta is in radians in this. So here theta is to be substituted in radians, and x degrees C is equal to how much? This much in radians. Okay. So use this to calculate the mass of that 5-gram needle. Sorry, that 5 centimeter long needle in whatever unit is appropriate, grams or milligrams or whatever. You can take the value of G as 10. Take the value of acceleration due to gravity as 10. Okay, so two people getting slightly different values. Let's check out. Okay. So as you can see from this vector diagram, we will get the relation that 2 times ft sine theta is equal to mg. Okay. So 2 times E into L into theta is approximately equal to mg, because I am taking surface tensile force as surface tension into length. Okay. And I'm taking sine theta as approximately theta, because theta is small. It is 7.5 degrees, which will become in radians. So it will become so m will become 2 times TL theta divided by G. So 2 into what was our surface tension? 125 millinewtons per meter. Convert that, okay, into what was our length? It was 5 centimeters into 3.14 divided by 24 divided by 10. Let's see what this works out to be. Okay. So I'm getting around 163 milligrams. Let's check out the value and the unit and everything. Yeah, 0.16 grams is approximately correct. Dhruv. Parth, I think there's a factor of 2 somewhere which has gone wrong for you. Otherwise, yours is also okay. So everything is in SI units here. This is in newtons per meter. This is in meters. This is in radians now. Okay. And this is in meters per second square. So you'll see you'll get the answer in Newton per meter per second square, which is kilograms.
So they have neglected the sign of theta, right? So
Okay, so this is one type of calculation that we do involving surface tension, where we are calculating tangential force at a surface using the definition of surface tension as force per unit length. Okay. So nothing more complicated than this. This is what that part of surface tension is about. Now the next thing associated with the surface and its elasticity we'll see is the what we call surface energy or elastic potential energy of a surface. So exploring this quantity will give us a second definition of surface tension also. Basically the elastic potential energy associated with a surface. Now the way to mathematically calculate this quantity is very simple, that if we create a surface out of a volume of liquid which hardly has any surface, okay, but we create a large surface out of it, then the work done by the external agent in order to create this surface will be stored in it as potential energy. Okay. So as usual, the definition of energy, the internal energy or potential energy of a system, is the work done by the external force against the internal conservative forces. So in this case, we can define the surface energy as the work done by an external agent against the internal conservative force, which is in this case surface tensional forces, to create a given surface. That is the surface energy stored in it. Okay, so this is equal to the surface energy of this given surface. Okay, so let us visualize a simple experiment to do this exercise. Okay, so suppose we have two thin glass rods, okay, which we are keeping very close to each other, but not exactly in contact, okay, neither physically nor mechanically. So neither we are pressing them against each other, so there is no normal reaction, so no mechanical contact, nor they are physically in contact because there's a small gap between them. Okay. So thin glass rods. Now the reason why we are selecting glass rods is because glass rods have high deal of what we call adhesive force with respect to liquid molecules. Now let's say we put some droplets of some liquid, like typically again we might use soap solution because it has high amount of surface tension as well as high amount of adhesive force. So these soap solution molecules cling on to the glass rods. So these are droplets of soap solution, basically. Now next what we do is, keeping one of the rods stationary, we pull the other one perpendicular to its length very gradually. So that creates a film of soap solution. If we do this gently enough and up to a certain degree, we'd be able to create a film of soap solution. But in order to do that, the external agent will have to, so this one is kept stationary. Fixed. Whereas this one is moved through a displacement of S, let's say. And thereby it creates a film of soap solution in between. Because on the one hand, the soap molecules, they cling on to the glass at the edge because of this strong adhesive force, but they also cling on to each other because of surface tensional force. So it creates a film of soap solution. So This is a thin film of soap solution. This is created because of two factors: the strong adhesive forces between glass and soap solution molecules, and the surface tension of soap solution. So these two factors allow this kind of situation to occur. So if you take a cross-sectional view of this situation, you will see that that looks something like this. To do a sort of magnified cross-sectional view of this. So these are our two glass rods. So you see that the thin film of liquid, its cross section will look like this. We magnified enough, you'll see that it's not that thin. Okay. So the thickness of the film, let's say capital D, is much larger than the thickness of a surface. So basically it has two surfaces.
So the thickness is molecule size, right?
Sorry?
The thickness is molecule size, right?
No, but the film is not that thin, beta. That's what I'm saying.
Okay,
The
okay.
surface is that thin. So this film is actually bounded by two surfaces on either side. You understanding my point? So if we magnify it enough, now what we'll understand that the film is a few microns thick, whereas a surface is, a fraction of a micron, like 1/100th or 1,000th of a micron, much thinner. So the film of liquid is more like a three-dimensional, cuboid of liquid, but albeit it's like a plate of liquid actually. It's like a plate of liquid, which is reasonably thin, but then not thin enough to qualify as a surface. So it is bounded by two surfaces on either side. Now this force that we are applying, in order to pull this second rod aside, that has to be balanced. That has to balance the surface tensional force. Because I'm pulling this very slowly. So it's going at acceleration tending to 0. So the work done by the external agent to create this film of liquid, to stretch out this thin film of liquid, is equal to the work done by this external force, which will be constant in magnitude.
Sir,
Yes.
can you please explain that last part again in which you wrote surface 1 and surface 2?
Yeah, see, basically what I'm trying to explain is that the thickness of this film, capital D, okay, this is the thickness of the film. It's very large compared to the thickness of a surface. Okay. So at a magnified level, when we look at the film of liquid, we have to visualize it like a plate of soap solution. You understanding my point?
Yes, sir.
So it is bounded by two surfaces. No?
Yeah.
Like even if you think of a thin sheet of glass, it has two glass surfaces. No? One on the front side you are seeing, one behind. Two
Right.
parallel surfaces. So same applies to the liquid surfaces that are bounding that thin film of liquid. Clear? No?
Yes, sir.
Okay, so now coming to the work done by this external agent, that work done will be basically this integrated from 0 to S. Okay, but this external force is balancing the surface tensional force, which is surface tension into the length of the glass rod. So let's take this length to be L. So this surface tensional force here, this surface tensional force, it is surface tension of the liquid multiplied by L. And because this is accelerating almost tending to 0, I mean, it's moving very slowly, so its acceleration is tending to 0. So you can see that the magnitude of the external force is equal to the magnitude of the surface tension force, T into L. So this becomes T into L ds integrated. So that's a constant. So that becomes nothing but T into L into S. But only one thing here, the total surface tensional force is double of this. Why it is double of this is because there are two surfaces. So this is very important over here. The net surface tensional force is equal to 2 times T into L because it is the net surface tension force due to surface 1 and surface 2. So both are separately applying forces. So you can see that there are these tiny force vectors on this surface on top, on this surface below. So the work done by the external agent, which is equal to the surface energy stored in the system, that equals to, just a second, that equals to this quantity. But now you can notice that L into S is the area of each surface, that is surface 1 and 2. So 2 times TLS or T into 2LS is equal to surface tension multiplied by total surface area. So this becomes the other important definition of surface tension, that the energy of a surface, the elastic potential energy of a surface, that equals to the surface tension multiplied by total surface area. So surface energy is equal to surface tension multiplied with surface area. E is the total surface area. So we get an alternate definition of the property surface tension over here now, that it is the surface energy per unit surface area. So we can also define just a second. Yes, as I was saying that we can also define the surface tension as surface energy per unit surface area. Okay, which is the same thing as tangential force per unit length. So whether we define it as surface energy per unit surface area or tangential force per unit length, is the same thing, which is surface tension. So as I was telling you earlier, there are two alternate ways of defining surface tension mathematically or as a physical quantity in terms of other physical quantities. And that is force per unit length or energy per unit area. Okay, so this is a very important aspect of surface tension. Surface energy being surface tension multiplied by surface area. Now, because of this, we observe a very important property of fluids, okay, or liquids in particular. So because surface energy is equal to surface tension multiplied by surface area, so hence any liquid body naturally takes a shape such that its surface energy, or hence surface area, should be minimized. Because when it is minimized, you have maximum stability. Any system has high stability when its potential energy or energy associated with internal conservative forces, that is at a minimum. So for example, droplets of liquid brought in contact naturally merge, or we use a more technical term, coalesce. Into a single larger drop, because surface area reduces and hence surface energy reduces, so the system is more stable. Another example is that in gravity-free environment, a volume of fluid will naturally take the shape of a spherical mass or a spherical volume. Because naturally or geometrically, a sphere has minimum surface area to volume ratio. So given volume of matter, we want to arrange it into a shape such that the surface area is minimum. Then it should be arranged into a spherical shape. So that is the reason why it might appear surprising how this happens, but in zero gravity environment, a volume of liquid naturally takes a perfectly spherical shape. Because again, the elasticity of the surface and those cohesive forces and all, they act in such a way to arrange it into a perfect spherical surface. And why it is, it has stability, or it achieves a sort of an equilibrium at that perfectly spherical surface, because the system is in such a state where its energy is minimized. So it's in an equilibrium state. It's in a stable equilibrium state. Okay, so two important aspects of surface tension. Surface tension being tangential force per unit length, and surface tension also being surface energy per unit surface area. Okay. So what we've learned so far about surface tension today.